Hi, my name is Michael Ibarra, and welcome back to part 2 of paint effects testing, where I look at aviation avgas and the effect on paint, especially with G100UL. If you find yourself here and have not watched my first video, please take a look at that first. It's linked in the description down below. First, some additional info and clarifications. Obviously, lots of discussion. Thank you for your criticisms and your compliments. Regarding fuel trucks, I intended to imply that Reed Hillview had a temporary issue of unknown origin, and that service did return within a week. This is not a hit piece, and I'm not a YouTuber looking for hits. This research and testing was initiated and all done on my own accord. I did not sauce the test fuel. I'm an engineer and a pilot with several ratings, and my day job is actually in flight test. My intent was to perform due diligence before introducing a new fuel to two personal aircraft. This was by independently verifying the reports of material compatibility issues noted in the field, and I'm freely sharing my learnings with the community. I will present to you additional observations of material compatibility and paint deterioration gleaned from continued testing. A quick recap and some important points. In my previous video, I shared results of testing 100 low lead and G100UL on painted surfaces and some wetted fuel components that had negative effects. In this video, I present results of additional material compatibility testing that I've performed. The aviation fleet is diverse in both aircraft type, composition, and age, which means every user's experience may be different with the use of a new fuel. I commend GAMI for taking on a unique challenge to develop a high-octane unleaded avgas for general aviation. I'm not able to test every scenario possible, but have gone beyond the average owner in attempting to assess my aircraft's compatibility with this new fuel. If one doubts the results that I'm presenting and they have G100UL available, I suggest and challenge you to perform similar tests to assess for yourself. If you want the TLDW, or short for too long did not watch, every single painted surface that I've subjected G100UL fuel samples to has had an adverse effect. Keep watching for all the details, and I apologize for it being so long, but everyone wants the data. Since the release of my first video, there's been quite a bit of discussion on the internet regarding the topic, and this is GAMI's response to me after I submitted them their maintenance form. I'm personally aware of 7 different aircraft that have noted issues in the field with paint deterioration. A Mooney at Watsonville that posted on Mooney Space, and I personally looked at on December 31st. A Cessna 421 at Reed Hillview that I've looked at several times. There's also a Mooney that posted on Mooney Space about paint deterioration around fuel drains and rivets at Reed Hillview. And in the first 2 weeks of January 2025, I've been made aware of 4 additional aircraft with paint damage. The first is a Piper at Reed Hillview that had some form of leak which then ate the paint in the fuel tank area and fuel drains. The second is a Cessna 172 at Reed Hillview that had stains and leaks from multiple areas of the aircraft which have compromised the painted surface. In this sequence of photos, you can see that the paint is heavily stained. Multiple surfaces on this Cessna have been compromised, including near both fuel caps on the top of the wing. One of the latest postings on the internet that's gained some attention is an RV-6 that I believe is based out of Watsonville. This is the first experimental aircraft I've seen post that has utilized G100UL and had possible issues. This aircraft has a fairly severe fuel leak, and as noted on the bottom of the fuselage, has some pretty good staining and paint deterioration. The operator posted that the only recent change in the past few weeks was utilizing G100UL. And just as I was putting the final touches on this video, I was put in contact with the owner of a Mooney at Reed Hillview Airport on January 13th, who noted that after recently topping off with about 20 gallons of G100UL, now has paint deterioration on the lower side of his wings. I don't have any photos just yet, but he did indicate that it's something that was not there when using 100 low lead. Now, in a couple online forums, there's been notes of paint staining, including a Skywagon in the North Bay and a Mooney at San Jose Airport. And to put this in context, only 2 airports currently carry this fuel in California, and they're about 30 miles or less from each other. I want to make it clear that the focus of my testing and this presentation is on the effect of G100UL and 100 low lead on both painted surfaces and materials, and not necessarily why or if any leaks occur. After the release of my first video, I was made aware that Textron put out a statement asking for more testing with G100UL. STS Aero Products also put out a service bulletin stating they do not currently approve of G100UL on their electronic fuel injection unit. Visiting Lycoming's website, specifically their fuels page, it highlights their philosophy toward aviation fuels. In late December, Eagle put out this document titled Clearing the Air, How Unleaded Aviation Fuels Gaining Approval, Part 1, which describes understanding the STC process and why it matters to aircraft owners. Needless to say, there's been a lot of questions running through my mind over the past month. Why is the fuel doing this to everything I test? Do I have contaminated fuel? Was Watsonville's fuel the cause? What about the fuel from Reed Hillview? Something just seems amiss. Progress since the first video. I continued to test the Cessna 182 panels that were painted with jet glow. After 8 days, there's no degradation I'm aware of to 100 low lead panel, and the fairing with G100 UL is close to completely stripped. I acquired a Randolph Ranthane finish part, which is new, never flown, and cut off of a Pitts special project. I drained a G100 UL sample, which is a 50-50 mix of 100 low lead, from an affected Cessna 421 and used it for my next test. I configured a Cessna 182 fuel selector, tested a small piece of fabric. I tested fuel primer O-rings in situ, and I did a lot of reading about O-rings. Finally, I tested, or better put, sacrificed, several more of my Cessna 182 inspection plates, and subjected them to 4 different fuel samples for side-by-side testing. First, let me show you what the panels from the previous video look like after 5 additional days of subjecting them to the respective fuels. What you see here is the Cessna 182 panels that were painted with jet glow paint. The G100 UL subjected panel continues to deteriorate, whereas I couldn't find any degradation in the 100 low lead. Noted above, you'll see the piece of fabric, and I'll discuss that in the testing later. So here's the final side-by-side of 100 low lead on the left and G100 UL when exposed to Sherwin-Williams jet glow Matterhorn white after 8 days exposure. And for completeness, this is the Cessna 182 panel subjected to G100 UL on December 31st. I had stopped testing with the camera and had not applied any fuel to it in several days. I'm not a chemist nor a paint expert, and whether the paint is being attacked by the fuel or it's the primer first, the end result's still unacceptable to me. This test brought up some valid questions about possible paint differences between parts. The G100 UL panel made me question the paint prep quality, as inspection panels are likely not paid as much attention as other parts of the aircraft, and I'll circle back to this later in the video. GAMI has continued to claim that G100 UL avgas is not a threat to normal aircraft paint, nor does it strip paint or damage the paint. And then in their next breath, they claim all high aromatic gasolines are hard on paint. I'm confused. After all, in the last video, I did show the logbook entry for the Cessna 182 where the aircraft was painted with jet glow Matterhorn white. So at this point, I must ask, what is normal aircraft paint? So I acquired a third paint sample. A friend is building a highly modified aerobatic Pitts, and he gave me a cutoff of a painted surface to test. This was painted with Randolph Ranthane finish, and my understanding is it was done at a highly well-respected paint shop in California.
So this is the panel off the Pitts, not flown yet. It's a cutoff from his work. Again, excellent paint. There's one and 2 sides that are bare metal. The others are painted over on the edges, and it looks like there's a primer coating on the bottom.
So I'll start testing this Randolph Paint Systems part, and I'll circle back to the results later in the video. So the local Cessna 421 that sparked my research continues to have paint degradation in multiple areas on the aircraft. For a second fuel sample to test and compare effects of on my painted surfaces, I drained fuel into 2 mason jars, one from each wing on the Cessna 421, to test against inspection plates previously subjected to 100 low lead. I figured that this was a good test to see if fuel from Reed Hillview acts the same way as my Watsonville sample, albeit this is an approximate 50-50 mix of G100 UL and 100 low lead, so it might take longer to have paint effects. Plus, this fuel was from an aircraft suffering paint staining and degradation with G100 UL. On the evening of December 28th, I drained some fuel from his aircraft out of both wings, and as you can see here, there's been degradation on the left-hand wing, and on the right side of the photo is the recent area of paint deterioration and discoloration that none of us believed was there about a week ago. The following videos and photos were taken on January 1st, 2025, and there are 3 affected panels in the lower right-hand wing of the 421 with staining and some paint curling on the edges of the seals. Going to the left wing, there's 2 panels in the lower surface that you can see here that are degraded. And note that my focus in this presentation is on the paint damage that's occurring and not necessarily the cause of the leaks at this time. The owner indicated to me that he's never had any paint damage like this where the paint's blistered or curled along the edges of these panels. To show how things have deteriorated over time, let me show an example of our observations on the left wing over a several-week span. Here's a side-by-side view of the lower left wing of the 421. December 15th, the left photo was taken, which was the first time I looked at the 421. The circular hatch has paint degradation and staining, whereas the oblong hatch in the background does not. Turning to the photo on the right, which was dated December 30th, the oblong hatch in the background actually has a paint issue now, and it was first identified on December 28th. The paint is blistering and there's staining on the hatch. Here's the hatch on January 3rd, 2025. This photo is a few days later, taken on January 5th, 2025. You can see that the paint is continuing to deteriorate. Then there's these two final photos I took, one on January 8th and the second on January 11th, 2025. So there's definitely some paint deterioration going on in the Cessna 421. In the first video, I performed side-by-side testing of inspection plates off of a Citabria and Cessna 182. The inspection plates exposed to 100 low lead had no noticeable negative effects. I took the fuel removed from the Cessna 421 on December 28th and applied it to the surfaces of the Citabria and Cessna 182 plates that were previously exposed to 100 low lead. After about 12 hours, I noticed paint deterioration on the Citabria plate, which had some paint cracks, and the Cessna 182 panel didn't take long to follow suit. Remember, as drained from the 421, this fuel is an approximate 50-50 mix of the two fuels. I'm theorizing that it may take longer to see paint effects since the G100UL is essentially diluted. Here you'll notice the fuel removed from the Cessna 421's right wing is utilized to test these two inspection panels. This is the Cessna 182 inspection plate, which previously had 8 days in 100 low lead with no issues. This is the Citabria inspection plate that previously been subjected to 100 low lead, and even with the chipped paint and cracks, had really no degradation with it. So some people ask about my test methodology. This is how I apply the fuel to each one. Use a small measuring cup. Here I apply 1 ounce to the Cessna 182 panel, followed by 1 ounce to the Citabria panel to start the test, and I'll slosh this around occasionally and add more fuel as needed. So take notice of the Citabria plate in the top left corner. On the left edge it starts sprouting a crack right about now, and the paint starts to deteriorate pretty rapidly. While difficult to see at this zoom level, the Cessna 182 inspection plate started to fray along the edges, and then degraded at about the 2-day mark. While it didn't deteriorate as fast as the Citabria panel, it's not surprising to me given that the jet glow paint's pretty resilient, but it goes to show that the fuel that was removed from the 421 will affect paint. Here's the two panels with the fuel removed from the Cessna 421 after about 4.5 days of exposure. As previously noted, the Citabria panel has an unknown paint origin, but had no negative effects when 100 low lead was applied to it. Now, let me show you the results of before and after for the Cessna 182 inspection plate. This is the Cessna 182 inspection plate previously subjected to 100 low lead on the evening of Saturday, December 28th, about 9 p.m. I then applied the 50-50 mix of the G100UL and 100 low lead from the Cessna 421 to it. The following 3 images were taken on the morning of January 2nd, 2025, and this is after 4.5 days of the Cessna panel being exposed to a 50-50 mix of G100UL and 100 low lead as removed from the Cessna 421 on December 28th. Obtaining fuel from the affected 421 and applying it to my test panels yielded similar results from previous tests. Given that it is likely diluted, it took longer to see effects as compared to the full 100% G100UL. This validated the results from the previous fuel sample I tested. Again, GAMI claims that G100UL will not damage paint, and I have verified that the fuel from the 421 does deteriorate painted surfaces. Since I was pivoting to my next test, I set aside this panel, but I did add about half an ounce of straight G100UL that I acquired from Watsonville to it, and this is the result of the paint deterioration 3 days later. The Project Pitts part that was painted with Ranthane Aviation paint got pulled out on January 2nd after 4.5 days of exposure. As you can see here, there are areas of paint along the edges that are deteriorated, both on the exposed side and on the painted edges. I believe this part was painted within the last 6 months or so, so it's a fairly fresh paint off the line, and it still seems to have deteriorated along exposed and rounded edges of the paint system. I set aside the sample and then moved the time-lapse camera to the next project, but here's some photos of the panel on January 4th and 5th for completeness. Okay, let's take a closer look at the part. The back side seems unaffected, and then where the peeling occurred on the one edge was a painted edge. However, I want to point out that edge was mostly submerged or subjected to the brown fluid that you see in the container, and that I have not added anything to this container in several days. And again, my theory is that whatever's evaporating is leaving the most aggressive components behind, and those aggressive components are what are attacking the paint and/or primer. So that test showed that a recent paint sample from a professional shop with Randolph product was fairly resilient. It does seem like the more resilient paints take at least 3 to 4 days to start showing deterioration. Don't forget that I'm trying to simulate what a slow leak would be like, by slowly adding small amounts of fuel to the container over time, and in the process, the highly volatile components evaporate, leaving the more aggressive, high boiling point items behind, and that's what I believe is causing the damage to the painted surfaces. Let me pivot now to showcasing one of the aircraft that had issues in the field. The first aircraft to report any potential issues with G100UL and its paint was a Mooney located at Watsonville Airport in California. On Tuesday, December 31st, I stopped by Watsonville Airport and located the Mooney that had reported the first paint issue I was aware of. This is a view of the underside of the right wing, which is severely stained, and the paint is severely compromised in many areas. For comparison, here's a few shots of the Mooney's left wing. So this should be an example of what the paint probably looked like on the right wing before the deterioration occurred. I didn't notice anything significant on the left wing, but the right wing here in these static shots you can see had significant paint damage and staining. And look at the damage here. Does this look familiar? There can continue to be discussions about the source of the leak in the Mooney and if the fuel may have contributed to it. But I think we can all agree that leaking fuel should not damage paint like this in our aircraft. I was able to speak to the owner of the Mooney on January 1st, 2025, and he stated that he got the STC on the 23rd of November, fueled up around the end of November with a total of 80 gallons over a week, and made several trips. Shortly thereafter, he started noticing the paint issues. While he had been waiting to get into the maintenance shop to inspect the issue, the paint continued to deteriorate to what you see here. The next topic was fabric. I located a scrap piece of cutoff from an AT-6 Texan's flight surface, and I exposed the opposite ends of the fabric panel to the two fuels, G100UL and 100 low lead. Limited exposure of this fabric panel showed possible degradation from G100UL. Other concerns are some paint deformations, bumps, and the fact that the fabric felt softer. I really think more testing is needed in this area from qualified personnel with the right tools and equipment. And these are the actual cans of the polyfiber aerosane utilized on that piece of fabric. For this test, I let the fabric make contact with the particular fuel at the base of the container. This is G100UL and it starts curling. After several days exposed to G100UL, I reoriented the fabric, cleaned the container out, and prepped for the next test with 100 low lead. This is the other side, which is 100 low lead, and you can see the fluid there kind of dripping off as it wicked up the fabric, but it had less curl than G100UL. Here's the fabric after testing it for about a week. On the right side, you'll see some bumps on the painted surface of the fabric. This is from G100UL. The 100 low lead side did kind of weep up it and cause it to be stained slightly, but this shows the G100UL side where the paint's blistered. And then we'll go to the left side here of it and show you. There is a little bit more flexibility on the G100UL side, but the 100 low lead is definitely stiffer. I do feel that more dedicated fabric testing should be performed, especially by personnel that have the expertise and tools to look at fabric over time. This is an example of a fuel sump drain in the lower fuselage of my Citabria. It's not uncommon for fuel to spray back up through the hole in the bottom, and that would be very difficult to remove and possibly could contaminate the fabric and/or paint system. And who hasn't spilled fuel while trying to bring the nozzle out of the top of their fabric aircraft? There's also other considerations like wing fuel vents that will spill fuel, which will make contact with portions of the airframe. So my question is, to what extent has G100UL been tested with fabric? Fabric is not currently listed on the FAQ on the G100UL site. A review of the G100UL AML shows numerous fabric-covered aircraft are listed. So after my O-ring test in the previous video, I wanted to dig into wetted fuel components, especially since GAMI said swelling of these is not an issue. So I located two primers, one from a Citabria and one from a Cessna 182. The O-rings are of an unknown age. And the installed O-rings measure at 0.511 inches, which is just above the nominal spec, and it might be because they're stretched when they're installed. I wetted the primers, kind of primed them a little bit and put them in a G100 UL container for testing. As you can see here, I accidentally spilled some G100 UL during this process. What's disappointing though is while the flammable cabinet is not aviation paint, it was instantly stained by the application of G100 UL. Here's the Citabria primer when I pulled it apart after about 5 days. As you can see, the O-rings are swollen, previously measuring around 0.511 inches. Again, not sure how old these O-rings are, maybe 5 years, and they've been sitting on the shelf. I'm going to set up and perform another test with new nitrile O-rings. Out of curiosity, I did attempt to put the primer back together, and while the video is sped up, the O-rings were loose, and I did break one of the O-rings in the process. And I don't know if the rubber was degraded or not, because I don't have the means to analyze it. The other primer from a Cessna 182 is shown here. This is a photo before I started testing, and as you can see, it appears that there is some form of lubricant on the O-rings. When I pulled the primer apart after several days, I noticed that there was a black kind of greasy gunk on the O-rings, and the O-rings were not swollen. Remember, I'm just trying to mimic the introduction of a new fuel to existing components in the field, and this got me thinking. A lot of repair kits for primers use seal lube, which is a silicone base. I've ordered a couple of these kits, and I'm going to retry this test with the unit cleaned and with fresh seal lube and without seal lube on it. As mentioned, I reran the primer tests with brand new O-rings and seal lube applied to one of the primers, specifically the 182. I didn't notice any issue with the silicone seal lube applied, but both O-rings were swelled to about the same diameter at 0.54 inches and change. I did reattempt to insert the primers back in with the swelled O-rings, and during the process I did chip and break one of the O-rings. Here's the second primer from the Citabria, and this again was oversized. I'm still personally concerned about nitrile O-rings with this fuel, especially ones that are buried deep in the fuel system, and time would only tell what would happen to them. There's another product most mechanics have in their toolbox called Easy Turn, aka Fuel Lube. Anyone that's used Easy Turn or Fuel Lube knows it's extremely difficult to remove from any surfaces, and it's basically impenetrable with 100 low lead. I devised another test where I took two MS nitrile O-rings and applied some Easy Turn to each one of them, and then submerged them in 100 low lead and G100 UL respectively. This photo is on January 5th at 3:10 p.m. when I started the test, and then later that night at 10 p.m. I started to notice that while the O-ring was swelling in G100 UL, there was kind of a dark color of fluid starting to settle at the bottom of the G100 UL container, while the 100 low lead remained unaffected. This continued into January 8th, where you can see that the fluid now covers the entire bottom of the cup. So for any of us that have used Fuel Lube or Easy Turn, you know it's basically impenetrable in 100 low lead. What I found out here is after 3 days, it basically deteriorated the fuel lube in G100 UL and turned it to a soft, pasty mush. And while there may not be a blob of this inside your fuel system, the fact that it fragmented it and turned it into a mush could be a concern if it goes upstream or downstream and clogs something in the fuel system. On the other hand, the Easy Turn lubricant that was soaked in 100 low lead for 3 days is basically as sticky as it was when it was first submerged. In fact, touching it with the X-Acto knife, it picked right up like the material does when it's new. And I didn't see any degradation in this container. These are the two O-rings after 3 days of testing, and on the left you'll notice the G100 UL O-ring had swelled significantly, while the 100 low lead one had not. Here's a collage of Easy Turn lubricant when submerged in 100 low lead and G100 UL over a 3-day span. You'll note in the lower right-hand corner of this collage that there's a third container of G100 UL and Easy Turn lubricant. I had put a larger component of Easy Turn on January 6th in this container, and over 2 days of testing, you can see that the material highly fragmented and basically came apart. Here's that same container of Easy Turn on January 13th after it sat for several days and the fuel evaporated some more. Easy Turn lubricant conforms to MIL standard G-6032, and it's regularly used in fuel systems by many mechanics, and also called out in some aircraft service manuals and service bulletins. I've listed some examples here. While I did not test the Easy Turn on top of an aluminum plate per the MIL standard, I suspect my findings would be the same, Where it would fail, several of the test conditions here noted with the deterioration of the easy turn lubricant. For completeness, and since GAMI recommends newer composition O-rings and seals, I tested some fluorosilicone O-rings. These particular O-rings are common on fuel caps on many aircraft. And as you can see here, the dimensions did not change much. The 100 low lead and G100 UL both had small amounts of swelling, and the G100 UL had slightly more swelling on the O-ring, but they were still very close in dimension. I also dug up a spare fuel selector valve for a Cessna 182 that I have lying around. This type of testing, I believe, would take several months to see the full effects of, and when I get some spare time, I might rig it, but for now I'm going to focus on other testing efforts. It's no secret that O-rings are a critical component of the wetted fuel system. Their technical handbook lays out tables to look up compatibility to different materials. Numerous chemical components within G100UL are unsatisfactory with normal nitrile O-rings. And to be fair, some of the components within 100 low lead don't have satisfactory ratings either, albeit they're in much lower concentrations. I added a column on the left that shows the compound compatibility rating from Parker, with 1 being satisfactory and 4 being unsatisfactory. X means insufficient data exists. To the best of my ability, I went and looked up some of the boiling points for respective components of G100UL, and those are noted in the center column, especially highlighted in yellow. As I theorized before, my belief is that the most volatile components of the fuel evaporate, leaving behind more aggressive items such as M-toluidine. These aggressive components are what I believe is attacking and damaging painted surfaces. Here's the STS from Chevron's 100 low lead product offering. I've compared the chemical compatibility ratings here just like I did with G100UL. Note that several are unsatisfactory. However, I'd point you over to the volume amounts of the fuel, which are vastly different than G100UL. Based on what I've learned, I wanted to address the AOPA Baron G100UL demonstration and its discussion about paint. Leaving the leaking bladder aside, and I left the link in the description, I believe there's more to this topic. They say a picture is worth 1,000 words. Review of the limited public photos over time for the Baron show what I believe to be early signs of paint deterioration after use of G100UL. Granted, some of the photos are highly pixelated and only focused on leaks, but they quote paint a picture. As they say, paint covers a multitude of sins. So do leaks. Due to it being a high-profile aircraft on display at Oshkosh 2024, the leaking fuel may have been removed early enough as to not cause widespread damage. However, before and after photos, in my opinion, show similar trends to the paint testing that I have performed, where paint deterioration starts at the edges of surfaces and spreads rapidly if not curtailed. These photos are from a report that GAMI supplied to AvWeb after the bladder leaks were noted at Oshkosh 2024 and some follow-on investigations. What I want to point out is the top left photo, which is before any major use of G100UL had started, and the paint condition there, note carefully. And the bottom left photo, while zoomed out and pixelated, shows the leakage, but behind that I think are areas of paint that had deteriorated and would have continued to deteriorate had the leak not been fixed. This is a screen capture from AOPA's report on the unleaded fuel demo Baron at 200 hours, and they talked about the leaks noted. But what I want to highlight here is the paint condition, and along many of the seams, while covered with leaks, I see evidence of the paint starting to deteriorate at the edges like I've seen during my testing. Based on these images and the note that they were really focused on the bladder leaks, I do think this overshadowed the fact that the paint was starting to deteriorate. To illustrate, let me do a side-by-side comparison. Look at the photo on the right from November 2023 when G100UL testing had recently begun. I see little, if any, paint missing or degraded. However, the photo on the left from Oshkosh 2024 shows stressed paint areas, including ruffled edges and missing paint along seams where fuel had been dripping and making contact. What I'm trying to point out is that the paint condition here is very similar to the symptoms I see when paint starts to peel during my testing. Eagle Fuel Cells put together a nice report on the leaking bladder investigation, and again here, I think the gooey mess covered up a lot of the paint deterioration that was starting. This is a zoomed-in view, and again, more ruffled edges, I believe, that are indicative of paint deterioration that shows up early on in my testing. These were photos taken at Oshkosh 2024 of the Baron. This is the left wing, and you can see some areas where I believe the paint has been compromised where the leaks were and was starting to degrade. Contrast that with the right wing of the Baron, which had 100 low lead. The paint doesn't appear to be peeling on any of the edges even though there was leaks. So it's my belief that had the leaks not been cleaned up regularly on the Baron, the left wing paint would have deteriorated more along the edges and seams. And I believe that the reason this really wasn't noticed is when you look at a large surface area, i.e. a whole airplane, you don't get into the macro scale. And since I've been doing testing on small parts, I'm noticing little nuances of what happens when the paint starts to deteriorate. So for one last comparison, look at the paint edges here along the seams. And now look at the recently reported RV6 with paint issues. I think it looks familiar. In the last few weeks, GAMI has since published some results from their paint compatibility testing. I would counter that based on my investigation and test results, that the tests they are showing, i.e. submersion in large amounts of fuel, are not representative of in-service scenarios. My tests show that drips and slow leaks lead to evaporation of the more volatile substances, which leads to likely paint deterioration. Take, for example, this test of a Cessna 182 plate, which had literally just been splashed with fuel and let to evaporate. And to use AOPA's Baron as an example, paint deterioration appears to be noted along seams and cracks along the edges of paint, not over big open surfaces, and the fuel has to evaporate in order to leave the more aggressive components behind. GAMI did release the time-lapse of their paint soak with several Bonanza panels. And as I mentioned earlier, I don't think this is a representative test of the issues that have been noted in the field where leaks cause paint deterioration. So, one more final test. To address some of the concerns about testing similar painted parts on multiple fuels, my 182 donated 2 more inspection plates permanently. I removed right-hand flap inspection plate covers, cut them in half, and labeled them A, B, C, and D for testing. I then placed them in 4 separate containers. A is G100UL obtained from Watsonville on the 15th of December. B is G100UL obtained from Watsonville on the 31st of December. C is 100 low lead utilized throughout my testing. And D is a mix of G100UL and 100 low lead, the 50-50 mix removed from the Cessna 421 on the 28th of December. The philosophy here is to expose different plates of the same paint origin to 2 different types of fuels each. So these plates were exposed for about 10 days to their respective fuels. And the deterioration started around 4 to 5 days for the majority of panels, with the exception of the 100 low lead panel. The 100 low lead panel remained unaffected throughout the entire testing. Let's look at the results. All the panels, with the exception of panel C, which was 100 low lead, had paint deterioration on them. This included the 50-50 mix from the 421 and the 2 distinct G100UL samples obtained from Watsonville in December. Further digging into the results, these containers were more constrained than the previous plastic containers I utilized, which elevated the parts. And I think because the parts were submerged in the fuel, they were delayed in paint degradation. Because the container size was limited, the fuel quantities added were at a slower rate than my previous tests. Surface preparation likely plays a role in the deterioration rate of painted surfaces. In my first video, the Cessna 182 panel deteriorated more rapidly, and in looking at the metal surface below it, I do wonder if it was not as adequately prepared as these. However, the end result was still the same, with the paint deteriorating in either case. One of my goals of this test was to see the effects of G100UL on random aircraft throughout the fleet. Granted, I can't go test everyone else's airplane, but I can take random panels from unknown paint origin and see what the paint effects are. And I will say that all of the panels I tested were affected to varying extents throughout the course of testing. Surface preparation likely plays a role in the variations of paint deterioration noted. Alright, let's summarize painted surfaces. To my initial statement, every single painted surface that I have subjected G100UL fuel samples to has had an adverse effect. Collectively, I've tested at least 17 painted surfaces, and all of them have been affected to some extent with G100UL. In addition to the Jet Glow Matterhorn white and the Randolph Ranthane paint, the silver panel in the lower left corner came off of a Warbird and was reported to be painted with Imron. On average, paint effects are seen around the 4 to 5 day mark for the more resilient paints. Issues tend to start at the edges of panels, whether it be holes, scratches, or chips. And I'll point out, there's likely no perfect plane other than the day that it possibly left the paint shop. Whether it is the primer being attacked first, and then that leads to degradation of the painted surface, in my opinion, this is an unacceptable behavior, and one that I am not willing to subject my aircraft to. Aircraft owners have extensive history and fleet experience with 100 low lead exposure to painted surfaces, to which any damage to these surfaces is extremely rare and well known. One of the hot topics in the unleaded fuel discussion is the role of voluntary consensus standards. Eagle has put out this document which discusses ASTM, the establishment of standards and fuel specs, and the FAA's role in the fuel specifications. I think it's interesting and educational for all of us to understand better what goes into the different pathways, specifically the PAFI program or an STC route like G100UL. I really do believe that voluntary consensus standards like ASTM D7826, which is a guide for evaluation of new aviation gasolines, are imperative as setting out proper test methods for development of fuels. Okay, let's summarize. Again, these are my personal observations and beliefs. Sadly, every painted surface that I have subjected to various methods of contact with G100UL has had a negative result. Damage could be caused by entry to the underlying paint attachment via seams, cracks, edges, etc., which ultimately results in separation and degradation. Something's amiss if GAMI cannot replicate this with their testing. Either it's the test method utilized, or the fuel that we have at Watsonville and Reed Hillview is different. Fuel samples obtained from both Watsonville and Reed Hillview have both shown the same adverse effects in my tested and painted surfaces. Nitrile O-rings do swell significantly in both constrained and unconstrained environments. Easy turn, aka we know as fuel lube, appears to be affected by contact with G100UL, whereas this did not occur with 100 low lead. This warrants further investigation and research. I believe that more testing of fleet-wide compatibility on materials is required, and encourage others to test my theories and results before use of such fuels. If it is necessary to replace any components in aircraft to operate G100UL, then I would argue that it is not a drop-in replacement for 100 low lead. And I'll root for all unleaded fuels that come to market, so long as I don't see adverse effects. And given the test results I've obtained over the past several weeks, I can't come to a conclusion that this fuel is compatible with the aircraft that I operate. As I mentioned previously, the FAA recommends that general aviation operators or mechanics utilize their service difficulty reporting system. And there's a great advisory circular on this, AC 20-109B, that explains it. Any users encountering issues with the product or part should report them to the appropriate manufacturer via direct contact or a dedicated reporting method. I encourage everyone to have a look at the resources on the next slide, as they are quite educational. On this page I've listed some references, and they're all linked in the video description below. I specifically encourage those who are not familiar with the background of unleaded avgas development to explore these references and more. Each one of them provides a unique perspective in the development of fuels and also has some technical information. I have highlighted 3 presentations here in this list that I think are especially worth taking the time to watch. I hope you find the information listed here in the report and these references useful, and thanks for watching.